All right, good afternoon, everybody. I know it's been a long day, so we're going to try and wrap this up as quick as we can. I'm Lauren Zeeb, and I'm the Transportation and Project Manager for Neapolitan Engineering. And along with Nick, our Structural Engineer, Roberto, our Geotechnical Engineer, and Jenna, our Water Resources Engineer, we are going to present our Silhavy and LaPorte intersection redesign. And with that, I'll pass it to Nick to talk about the intersection background.
Thank you, Lauren. So as a team or a company of Neapolitan, we were tasked by the city with the redesign of the Silhavy and LaPorte intersection in Valparaiso. Our services were primarily requested due to the increased traffic volume in this intersection and due to safety concerns. Currently, this intersection is the third most dangerous intersection within the city limits. With that goal in mind, we broke down our project into four main elements. These include the realignment of our roadway to be handled by our transportation engineer, design of a safe pedestrian passageway handled by me, our structural engineer, design of a stormwater management system handled by our water resources engineer, and geotechnical design as needed to support the other disciplines. So if you look at the aerial photo all the way to the left, you can see the project site back in 1952. Here the Silhavy Road runs north-south and LaPorte Avenue runs east-west. And you can see back in 1952, it's mostly surrounded by farmlands, few residential buildings here and there. Moving on to 1998 came the expansion of State Road 49 to the east of our project site. Along with this, the LaPorte Avenue portion of the intersection was expanded, and you can see some commercial development to the south of the intersection. Moving on to 2003, you can see the Valparaiso Walk and Valparaiso Marketplace commercial areas have been completed. There was no expansion of the roadway at this time, and that's where much of the additional traffic volume came in this time. So taking a further zoomed out look, you can see the project site, Silhavy and LaPorte intersection, is located on the east side of the city. Valparaiso University is right down here. It's in close proximity to State Road 49, which runs north-south, State Road 2, three major commercial areas as seen in red here, and a major residential area seen in blue. And with that, I'll hand it off to our geotechnical engineer, Roberto.
Thank you, Nicholas. Now, before designing, we conducted a soil analysis to determine what soil types and soil parameters we were going to work with at our site. This was completed utilizing soil boring logs provided to us by the owners, whereas we determined that the composition was primarily a clay loam, around 6 to 11 feet, and sand around 20 to 35 feet, depending on the soil borings. Now, this is just a figure showing how we utilized the data to construct a figure that was more easy to understand, where it just gave us the elevation of each soil layer. Now, with that, I'd like to pass it on to our transportation engineer, Lauren Zeeb.
Thank you, Roberto. So with the transportation aspect, a few different design alternatives were considered in the first semester. So here you can see this roadway has two left turn lanes, so that was one of the alternatives looked at, adding an additional left turn lane on LaPorte Avenue on both sides of Silhavy. And then another alternative was a roundabout with a single entry and then two circulatory roadways. And then lastly, the one that we chose to do was a roundabout with double entry lanes and then two circulatory roads in the middle. The biggest concerns with the transportation aspect were cost, safety to both vehicles and pedestrians, along with the effectiveness, so the volume to capacity, so how many cars you can actually get through the intersection versus the volume that you have, and then also user delay, which ties into the vehicular emissions, because the longer you sit and wait, the higher your emissions are. So this is an overview of the roundabout that I designed. And so as you can see here, there's a bypass lane, and there's only one of them. This roundabout design improves safety, capacity, and it reduces delay, so it helps save time and money. Rodel was a computer program that was used to help determine the level of service for both the construction year and also the design year, which is 20 years out in the future. And so the roundabout goes from being a level of service of A to B, which is totally acceptable over a 20-year lifespan, and the delay goes from about 9 seconds per vehicle to about 15 seconds per vehicle. The biggest question I wanted to answer was why a roundabout? Roundabouts are safer than a regular signalized intersection, and the biggest reason why is because there are less conflict points. So as you can see here, there are only 8 circles, so those are those 8 conflict points, whereas an intersection has 32. Roundabouts are safer, but that doesn't mean there aren't any accidents, they're just less deadly. So you don't have a T-bone occur in a roundabout. It's usually fender benders, things like that, so they're a lot safer that way. And as you can see in this chart here, it's just comparing different countries and the percent reduction in all crashes being 35%, and then 76% in injury crashes. And then, so for it to actually being built, there were a few different considerations. A maintenance of traffic. So there are 2 different phases that I came up with. One being the north and west side being completed first, so that would be closed to construction and the traffic would flow east and south. And then once the north and west was totally constructed, it would flip, and then the east and south would then be closed to complete the roundabout. And then also what was considered was a truck detour. With construction zones, they're usually smaller to allow for safety for the workers and everything. So getting a truck through a construction zone is not the most ideal situation. So the trucks that were considered were those coming off of State Road 49. And so basically what would happen is they would have to continue all the way to the US 30 exit and then onto US 30. And then they have 2 different choices, whichever one they want to choose. They can take this green path, which will have them turn left onto Sturdy Road, go through the other roundabout, and then continue onto LaPorte Avenue, and then they have access to this commercial area. Or they can go up to US 30 and turn right onto the Silhavy Road and follow this windy path, and then also lead up to the commercial area. The green path is the ideal path because there's less curves for a truck. And then lastly, this is a little drive-through of the roadway. And so basically, you're just driving through the outer lane of the roundabout, and then you are now entering the roundabout, staying in the outer lane, following along, and then you are exiting again in the outer lane as well. And then that's it. And then with that, I will pass it off to Nick, our structural engineer.
Thanks, Lauren. As the structural engineer, my main task was to develop a safe pedestrian passageway. The other main goals handed to us by the city were to meet community standards for architecture, provide pedestrians with a safe passageway through the intersection, increase foot traffic in and around the project site. So currently, as this intersection is signalized, it's not a very attractive intersection for pedestrian and foot traffic. So one of the main goals with the structural discipline was to increase this traffic in and around the site. I considered multiple span alternatives, but wound up settling on a span that goes from the northwest to the southeast of the site. This span provides pedestrian a safe passageway over the busiest roadway section, which is LaPorte Avenue, and it's also compatible with the design of other disciplines. I also considered 4 structural system alternatives. These included a tunnel, a cable-stayed bridge, a tied arch bridge, and a truss bridge. My ultimate deciding factor for determining a final system were aesthetics, and this is a structural example that I used. It's a Dry Creek pedestrian bridge in Denver, Colorado, which was an effective solution for that project site. So moving on to the tied arch system, first of all, it's compatible with other disciplines. It's also an aesthetic design. And one unique thing about this arch system compared to other traditional arches is that the actual arch doesn't transfer any lateral loads into abutments. Traditionally, abutments are constructed with earthwork, and lateral loads from the arch are then transferred into the ground through these abutments. In this system, the lateral loads are transferred directly into the deck. So all substructural elements, which are the bridge columns, only have to handle vertical forces. This decreased the amount of land that we had to acquire for the site and allowed our supports to be effective in a very limited area. Additionally, we used elevator bridge approaches as opposed to ADA compliant ramps. These elevators are, of course, ADA compliant, but ADA compliant ramps required such a gradual slope that it would have required additional land acquisition. So once the bridge geometry was determined, it's a 200-foot arch span. The geometry was modeled using RISA structural analysis software. This was then loaded in accordance with ASHTO LRFD bridge and pedestrian bridge specification standards. These are national standards which dictate the type, magnitude, and combination of loading onto bridge structures. And then finally, based on these loading conditions, standard members were selected using the American Institute for Steel Construction Manual. And with that, I was able to develop an effective pedestrian passageway system that was compatible with all sub-discipline designs. Now I'll hand it off to our water resources engineer, Jenna Meert.
Thank you. Okay, so I designed all of the stormwater management systems for the site. And so anytime you redesign a site, you have to meet the new city ordinances and drainage standards. So those primarily broke into two different volumes of water. One, a flood control volume that had to be detained on the site to prevent flooding downstream, and the other, a water quality volume, which needed to go through certain treatment processes to remove total suspended solids, which is just sediment in the water, as well as certain nutrients like phosphorus and nitrogen to prevent algae blooms downstream. So just an overview of the system we had. It was 4 main components. So there is the piping system that collected the water along the roadway and transported it between the different elements. There are 2 vegetated swales along the western portion of the roadway, a rain garden in the center, and some underground infiltration chambers here. The water quality volume was primarily treated using the vegetated swales in the rain garden, and the infiltration chambers were primarily for that flood control volume. So this is just an overview of the watershed used. So any water that falls on that shaded region was the responsibility of our stormwater management system. And the different colors just show which element of the system the water went to first. So this is a kind of a schematic of what the vegetated swales might look like. We designed them for the mode condition in case the owner preferred that aesthetic or that type of maintenance. But the unmowed swale like this is more recommended because it treats the water better, it slows things down more. So the water would come off of the roadways and down the swale and then overflow into the storm sewer system. This is an overview of the rain garden in the center of the roundabout. So it has the side slopes and then a ponding area in the middle. We also were bringing water into the rain garden through concentrated pipes from that storm inlet system. So that water had to be redistributed out so that there weren't erosion problems. So we have 2 level spreaders in the rain garden as well, just to spread that flow back out. And then the soil in this area was not compatible for infiltration. So we have an under drain system similar to this one shown here to collect the water at the bottom of the rain garden. And then the final component are the underground infiltration chambers. And this video is just going to kind of play as I talk, showing you how they operate. But the infiltration chambers go underneath the parking lot. The parking lot we selected is shown here, north of Noodles and Company and south of Aldi, and here's the intersection. And we did this primarily because there's not a lot of area around our intersection for traditional detention. So going underneath the parking lot gave us space to detain this water. So the water goes through under into the chambers, and then it kind of fills those chambers up and will infiltrate back through. And so we'll let the video play. It'll show kind of the overflow system as well. So it fills this first chamber first, and that's wrapped in a geotextile to help remove additional sediment. And then it will overflow, as it's about to show. I'm a little ahead of my video there. Overflow into the manifold system for a larger storm so that it just disperses into the chambers more quickly. And then it would eventually outlet if necessary, but that's only going to be necessary for the much larger storms. And then we also chose this parking lot because it's not used very much right now. We made an agreement with the land users to put an area for future development in the parking lot, so there is a space available for about a fast food sized restaurant if they decide to develop it in the future. But for now, it's not too much of an economic problem to decommission the parking lot temporarily because we can replace it, and it's not being used currently. So with that, I'm going to pass it off to our geotechnical engineer, Roberto.
Thank you. As our structural engineer, Nicholas Schur, mentioned previously, the scope for the geotech was to assist in the other disciplines, which resulted in designs of the pavements for the roadway and the parking lot, the bridge foundation, and the elevator pit, which included a foundation wall and slab. Now for the roadway pavement, we initially looked at either using a concrete or an asphalt. An engineering decision was made, and we chose to go with a concrete. So the selection was a Portland cement concrete. We designed it for a 20-year rigid forecast, and that resulted in the slab being 12 inches thick. This elevation view, you can see the 12-inch slab has a subgrade treatment of type 2, which is just 6 inches of the subgrade were replaced and substituted with an aggregate, which would assist in the whole design. For the parking lot pavement, we stuck with asphalt, and we designed it with a hot mixed asphalt or HMA surface, and under that would be a 3-inch HMA base. We applied a 2% grade onto it so that the runoff could go into the underground infiltration basins that our water resource engineer talked about earlier in the presentation. Now for the foundation, we were looking at either using a spread foundation, a spread footing, which is in here in this image, or piles, which are piles just driven into the ground, where the structure would be placed on top of. When we calculated the results using the parameters of the soil, it resulted in the base being a 15 by 15 and having a 30-inch thickness. For the foundation walls, it was an added scope for the elevator pit later on in the project, so there weren't any really alternatives that we looked into. We designed the foundation walls as retaining walls, and utilizing the soil parameters once more, we determined that the stem height would be 5 feet, and the thickness of the stem would be 12 inches, and the base would be 8 inches. For the slab, the sizing was based off average elevator shafts, so that gave us a 9 by 9 slab, onto which it was 6 inches thick and would be placed on top of those foundation walls. And with that, I will talk about the construction cost. We estimated it to be about $5.6 million, with the breakdown here shown here. The transportation and geotechnical, we shared the cost with being around $4 million. The structural, $400,000, and the water resource, $1.2 million. And with that, I would like to invite the rest of my group up for any questions, and thank you guys for listening.